Welcome back. Let's practice finding curvature of space curves. All right, so here's our first example. We want to find the curvature of the curve where s is the arc length parameter. And our vector function is r of s is equal to the quantity 1 plus the square root of 2 divided by 2 times s times I plus the quantity 1 minus the square root of 2 divided by 2 times s times j. Okay, so when you want to calculate the curvature of a curve, there's actually 4 different formulas you could use. And they look like this. Now, I know that this can be a little overwhelming at first, but each of these formulas have specific cases where you want to use them. And so while you might be worried at first about choosing which formula to use, in most scenarios, only one of them is going to pertain to your particular problem. And so let me go through these formulas one by one and tell you when we want to use each of them. By the way, I show you where these formulas come from in the lesson video for this topic. In this video, we're just going to focus on using them. But starting with this formula right here, this is actually known as the definition of curvature. And this formula is particularly useful when you were given a vector function that is already parameterized using the arc length parameter s. Right? So if you have a vector function r of s, where s is the arc length parameter, you have to know that. You can't assume that it's an arc length parameter. You have to be told that it is. But assuming that that is true, the curvature k would be equal to the magnitude of the derivative of the unit tangent vector with respect to s, the arc length parameter. All right, so another way to write that would be the magnitude of the derivative of the vector function capital T of s, where the vector function capital T is the unit tangent vector, or another way to write that would be the magnitude of the second derivative of the vector function in terms of s. Okay, I talk about why this is true in my lesson video. I'm not going to get into the details about that here. Okay, so once again, this formula you should only use if you were already given a vector function in terms of the arc length parameter, or if you were already told that you have to reparameterize your vector function in terms of the arc length parameter. Okay, if you have to do that, then you might as well use this formula. But if you don't have to reparameterize, and your vector function is in terms of another parameter, such as t, then these two formulas down here are going to be your friends. If you're given a vector function r of t, most commonly you will use this formula right here. The curvature k is equal to the magnitude of the derivative of the unit tangent vector in terms of t divided by the magnitude of the derivative of the vector function. The majority of problems where you will calculate curvature, this will be the formula that you use. However, you could also use this formula right here, which says that the curvature is equal to the magnitude of the cross product between the first and second derivatives of your vector function, all divided by the magnitude of the first derivative of the vector function cubed. And this formula is particularly useful when your vector function has components involving polynomial expressions, such as t squared, t cubed, t to the power of 4, whatever. If you don't see trig functions or exponential functions or logarithms and just see simple algebraic components, this formula should be your go-to because those components work very nicely with the process of a cross product. Okay, if you have trig functions or exponential functions, or really anything that's going to involve a chain rule or a product rule, when you take the derivative once or even twice, then the cross product is going to get extremely messy, and so you want to avoid that. Just use this formula over here. Okay, so those are the second and third formulas for curvature, and now finally, there's one more, or at least one more common one. Technically there are more, but these are the 4 main formulas that you will use. This formula is for when you are given a plane curve defined by a function. If you are given a plane curve represented by y equals f of x, then you can find the curvature by taking the absolute value of the second derivative of the function, or y double prime, divided by the quantity 1 plus the first derivative, y prime, squared, and then you take that quantity to the 3/2 power. So each of these 4 formulas have specific cases where they are helpful. All right, so I know I spent a lot of time on this, but I want to make it very clear that although there are a lot of formulas for curvature, they are not all always going to be useful, and it's usually pretty clear, given the information about your curve, which one of the formulas you should use. Okay, so let's go back to our example. Here we are given a vector function that is already in terms of the arc length parameter s, right? We have r of s is equal to these two components in terms of s. So what we want to use here is that formula for the definition of curvature that involves the arc length parameter s. It looked like this. What we're going to do here is take the magnitude of the derivative of the unit tangent vector in terms of that arc length parameter s, which also happens to be equal to the second derivative of the vector function in terms of s. Okay, so really what we want to do here is take the derivative of this vector function twice, take the magnitude of that second derivative vector function, and that will be equal to the curvature k. All right, so let's do that here. Let's start with the first derivative, r prime of s. We want to take the derivative of each of these components individually with respect to s. And so starting with the x component, the derivative of 1 is 0, and then we just have s to the first power, so the derivative will just be its coefficient. So we have the square root of 2 divided by 2 times I, plus the derivative of the y component, which once again, the derivative of 1 is 0, and then the derivative of s to the first power will just be its coefficient, which is the negative square root of 2 divided by 2. So really, instead of plus, we will have minus the square root of 2 divided by 2 times j. All right, so that's the first derivative of our vector function. Now let's find the second derivative, which is r double prime of s. That will be equal to the derivative of these two components, which are both constants, right? The square root of 2 divided by 2 and the negative square root of 2 divided by 2. Both of those components are constants, so both of their derivatives are 0. So we get 0i plus 0j, which ultimately means that the second derivative of our vector function in terms of s is the 0 vector. Both of the components are 0, so it is just the 0 vector, which means that when we go to calculate the curvature here, we're going to be taking the magnitude of the 0 vector, which is just 0. The 0 vector doesn't have a length, it has no magnitude, it is just 0. All right, so the curvature here is equal to the magnitude of r double prime of s, which this is a little redundant, but I'm going to write it out here. You would have the square root of 0 squared plus 0 squared, which is equal to 0. The curvature k is equal to 0, and that is the final answer to this problem. Okay, and so conceptually what that means, the fact that the curvature is 0 for this curve, means that it's a line, right? If your entire curve has 0 curvature, then it doesn't curve at all. It is just a straight line. Okay, let's take a look at another example. Here we once again want to find the curvature of the curve where s is the arc length parameter. And our vector function r of s is equal to 2 times cosine of s divided by the square root of 5 times I, plus 2 times sine of s divided by the square root of 5 times j, plus s divided by the square root of 5 times k. All right, so just like with our previous example, our vector function is given to us already in terms of the arc length parameter. So there's really only one option here for what formula we should use. We want to use that definition of curvature. We're going to be using the same exact formula we used in the first example. All right, so we're going to take the derivative of our vector function in terms of the arc length parameter twice, and then take the magnitude of that second derivative vector. Okay, so starting with the first derivative, r prime of s will be equal to the derivative of each of these components individually. And you'll notice that for the two trig functions, we have an inside function that is not just s. So we will need to use the chain rule here. We're going to take the derivative of the outside function and then multiply by the derivative of the inside function. And so the derivative of cosine is negative sine. So we get negative 2 times sine of s divided by the square root of 5. And then you want to multiply by the derivative of that inside function. The derivative of s divided by the square root of 5 is 1 divided by the square root of 5. So we're multiplying by 1 divided by the square root of 5. And don't forget that that is all multiplied by I. And before we move on to taking the derivative of the y component, I am going to combine these constant multiples. Just multiply negative 2 by 1 divided by the square root of 5 and keep it out front. So here's how I'll rewrite this. We'll have negative 2 divided by the square root of 5. Okay? And then that's multiplied by I. But then if we take the derivative of the y component, the derivative of sine is cosine. So we have plus 2 times cosine of s divided by the square root of 5, but once again, you want to multiply by the derivative of that inside function, which will just be 1 divided by the square root of 5 again. So I'm going to multiply it out front, and we'll have 2 divided by the square root of 5. All right, that's multiplied by j, and then you want to add that to the derivative of the z component, which will just be 1 divided by the square root of 5, and multiply it by k. Now, let's take the second derivative. We'll have r double prime of s is equal to the derivative of these components. We will have to use the chain rule again. We will have to multiply by the derivative of these inside functions. So don't forget to take care of that with each of these derivatives. Once again, the derivative of sine is cosine. So we have negative 2 divided by the square root of 5 times cosine of s divided by the square root of 5. But then I'm going to multiply by the derivative of that inside function again, which is 1 divided by the square root of 5. And I'm just going to multiply that right into the coefficient right here. So really, we're multiplying by that value, but 1 times negative 2 is negative 2, and the square root of 5 times the square root of 5 is just 5. So we don't need this here. We can just rewrite that denominator to be 5. Okay, that's all multiplied by I, and then you want to take care of the y component. The derivative of cosine is negative sine, so we'll have minus 2 divided by the square root of 5 times sine of s divided by the square root of 5. But once again, you want to multiply by the derivative of that inside function. So we're going to be multiplying by 1 divided by the square root of 5 again. So this coefficient out front will just become 2 divided by 5. All right, that's multiplied by j. And then we want to add that to the derivative of the z component, which in this case is just a constant. So the derivative is 0. So we have plus 0k. All right, so we now have the second derivative of our vector function in terms of the arc length parameter. So we can now find the curvature of the curve that this vector function represents by taking the magnitude of that vector function. The curvature k will be equal to the square root of the sum of the components squared for r double prime of s. Now, the z component is 0, so we don't need to worry about that. We just have to focus on the x and y components. So we're going to square both of them, which means we have negative 2/5 times cosine of s divided by the square root of 5 quantity squared plus negative 2/5 times sine of s divided by the square root of 5 quantity squared. All right, now simplifying, we will get the square root of 4/25 times cosine squared of s divided by the square root of 5 plus 4/25 times sine squared of s divided by the square root of 5. Okay, so we just squared both parts of these terms. We squared negative 2/5 to get positive 4/25, and we squared cosine to get cosine squared of that inside function. And the same thing over here. We squared this coefficient, and we squared sine. Now, to simplify, you want to pull out that common factor of 4/25. And so if we do that, you get the square root of 4/25 times cosine squared of s divided by the square root of 5 plus sine squared of s divided by the square root of 5. Now here's why that was important to do. What we have here is an expression that is equal to 1. All right, remember the Pythagorean identity for sine and cosine. Cosine squared of an angle plus sine squared of that same angle is equal to 1. All right, so really what we get here is the square root of 4/25 times 1, and anything times 1 is itself. So we have the square root of 4 divided by 25, which gives us 2/5. 2/5 is the value of the curvature for the curve represented by this vector function. It is important to notice here that that curvature is a constant value, so the curvature doesn't change depending on where you are along the curve, which is pretty interesting, but that is the result that we found here. Okay, let's take a look at another example. Next up, we want to find the curvature of the space curve, and our space curve is given by the vector function r of t, which is equal to 6ti plus 8 cosine tj plus 8 sine tk. Okay, so this time around, our vector function is not given to us in terms of the arc length parameter s. It's just in terms of some other parameter t, so we're not going to be using the same formula that we used in the first two examples. Instead, we're going to make use of one of those two other formulas that are useful when a vector function is given in this way. Now remember that there was one involving a cross product. That one is most helpful when your vector function involves all polynomial components. And if you look at the components of this vector function, we have some trig functions, so I don't think we want to use that formula, which means the formula that we will use is this one. The curvature k is equal to the magnitude of the derivative of the unit tangent vector divided by the magnitude of the derivative of the vector function. Okay, so let's get started. Let's start by finding the derivative of our vector function. We'll have r prime of t is equal to a vector whose components will be the derivative of these components. The derivative of 6t is 6, so we have 6i plus the derivative of 8 cosine t, which the derivative of cosine is negative sine, so I'm going to erase that plus sign. We'll have minus 8 times sine t j, and then the derivative of sine is cosine, so we have plus 8 times cosine t k. All right, so that's the first derivative. We will need its magnitude to calculate the curvature, but not only that, we need its magnitude in order to find the unit tangent vector whose derivative we have to find, right? Remember that the unit tangent vector, capital T of t, is equal to the derivative of the vector function divided by its magnitude, okay? So finding the magnitude of this derivative vector is dual purpose. We really need to find that magnitude. So let's do it right now. The magnitude of r prime of t will be equal to the square root of the sum of the components squared. So we'll have 6 squared plus negative 8 times sine t squared plus 8 times cosine t squared. All right, so squaring all of those components right away, we get 36 plus 64 times sine squared t plus 64 times cosine squared t. All right, I hope it's okay that I skipped the step of showing that we're squaring these components. To save a little bit of time and work, I'm just going to square those components right away. Now, what you want to do is pull out that common factor of 64 from sine squared t and cosine squared t, because that's going to create something very nice for us. This will be equal to the square root of 36 plus 64 times sine squared t plus cosine squared t. And we know from the Pythagorean identity for sine and cosine that sine squared t plus cosine squared t is equal to 1. So this is equal to the square root of 36 plus 64 times 1, but anything times 1 is itself, so we just have 64, and 36 plus 64 is 100. So we get the square root of 100, which equals 10. All right, so that is the magnitude of the derivative of our vector function. So now let's use that along with that derivative to write out the unit tangent vector, because then we will have to take the derivative of that vector and find its magnitude. Okay, so the unit tangent vector will be equal to this vector, but where all of the components are divided by 10, the magnitude of the derivative of the vector function. So we'll have 6 divided by 10 times I minus 8 divided by 10 times sine t j plus 8 divided by 10 times cosine t times k. All right, I had to squeeze that in there, but again, it's just this vector, but where each component is divided by 10. Now, I will simplify a little bit. 6/10 is the same as 3/5, so we have 3/5 times I, and then 8/10 is the same as 4/5, so we have 4/5 times sine t j plus 4/5 times cosine t times k. All right, so now it's a little bit easier to see what that vector is, but now we have to take the derivative of that unit tangent vector. So let's do that here. The derivative of the unit tangent vector will be equal to the derivative of these three components. The x component is a constant, so the derivative is 0. So we have 0 times I plus the derivative of negative 4/5 times sine. The derivative of sine is cosine, so we keep that negative sign. We have minus 4/5 times cosine t times j, and then the derivative of the z component, cosine's derivative is negative sine, so we have minus 4/5 times sine t k. All right, so now our last step here, before we can calculate the curvature, is to find the magnitude of this vector. So we will take the magnitude of t prime of t, which means we will take the square root of the sum of the components squared I'm going to ignore the x component since it's 0, 0 squared, and adding that to the other components doesn't do anything. So we're just going to be squaring these two terms and adding them together. Squaring 4/5 gives you 16/25. So we have 16/25 times cosine squared t plus 16/25 times sine squared t. All right, now once again, very similar to what happened over here, both cosine squared t and sine squared t have a common factor. You can pull that out, and what you're left with is cosine squared t plus sine squared t, which from the Pythagorean identity for sine and cosine is equal to 1. So you're just going to be left with the square root of 16/25, which is 4/5. Okay, so now we're almost done. We have both the magnitude of the derivative of our unit tangent vector and the magnitude of the derivative of our original vector function. So we're going to take 4/5 and divide it by 10. All right, k is equal to 4/5 divided by 10. And so you just want to multiply those denominators, and you'll get that k is equal to 4/50ths, which reduces to 2/25. So I'm just going to erase that. You will find that k equals 2 divided by 25. All right, that is the curvature of this space curve. In fact, it's a constant curvature, which means that every single point along this curve has the same exact curvature. The curve does not bend more sharply or less sharply at any point compared to another. The entire curve curves in the same way the entire time. The curvature is constant. Hey there, real quick, before we take a look at the next example, if you find my tutorial videos here at JK Math to be helpful, then I'd like to invite you to join my membership site, JK Math Plus, where you get access to many perks, including bonus content and my exclusive community. The bonus content includes dark mode versions of my videos, extra example problems, and more, while the community is a private space online where you can post questions, have discussions, and study together with me and other members. To learn how to join and see a full list of everything you get access to as a member, you can head over to jkmathematics.com/plus. I'll have a link for that in the description of this video. So if you are interested in becoming a member, feel free to check that out. It's a great way to support me and the tutorials I make, as well as a great way for you to learn math better. But for now, let's take a look at the next example. For our next example, we want to find the curvature of the space curve in terms of t and the curvature at the point 1, 1, 0. Okay, so we have two missions in this problem. We first want to find a general expression in terms of t that represents the curvature of the space curve, but then we want to find the specific curvature at a particular point, a point that has coordinates of 1, 1, and 0. And that point is on this curve represented by this vector function. R of t is equal to e to the power of 2t times I plus e to the power of 2t times cosine tj plus e to the power of 2t times sine tk. And so before we do anything here, I do want to figure out what value of t this point corresponds to, because when we get our curvature in terms of t for the space curve, it is going to be in terms of t. So we can't plug in this point to get the curvature. We have to plug in the value of t that corresponds to this point. So the easiest way to do that is to just set one of the coordinates equal to the corresponding component of the vector function. So in this case, I'll pick the x coordinate. We'll set it equal to the x component. We'll do a little side work here. We'll have 1 equals e to the power of 2t. And so the only way this is true, you could solve it using the natural logarithm, but thinking about it logically, the only way that this happens is if e is being raised to the power of 0. Okay, that's the only way that this becomes equal to 1, because anything to the power of 0 is 1. So in order to have e to the power of 0, t would have to be 0. 0 times 2 is 0, so then you'd have e to the power of 0, which is 1. Okay, so that's the only way that that happens, which means that this point corresponds to t equals 0. So once we get our expression for the curvature in terms of t, all we have to do is plug in 0, and that will give us the specific curvature at that point or at that value of t on the space curve. Okay, but now let's actually work on finding the general expression for the curvature. Looking at our vector function here, it's not in terms of the arc length parameter, so we're not going to use that formula that we used in the first two examples. We're not going to use the definition of curvature. And the components are pretty complex, right? We have trig functions and exponential functions, so you don't want to use the formula involving a cross product that will get very nasty very quickly. And our vector function is not a plane curve given to us in terms of f of x, right? We don't have a function y equals f of x, so we're not going to use that other formula that we looked at. The only option here is to use the formula that we just used in the previous example. This formula right here, that the curvature is equal to the magnitude of the derivative of the unit tangent vector divided by the magnitude of the derivative of the vector function. All right, once again, this is the formula that you will use most often when calculating curvature. And so let's get started. There's a lot of steps to this problem, and our vector function is not very nice. So there is going to be quite a bit of work involved with this. So strap in and get ready, because we're going to be here for a little bit. Let's start with the derivative of our vector function. We need to find r prime of t. Starting with the x component, the derivative of e to the power of 2t will be 2 times e to the power of 2t. Right? The derivative of an exponential function e is itself, so we have e to the power of 2t, but don't forget to multiply by the derivative of the exponent, so that's where that 2 comes from via the chain rule. All right, that's multiplied by I. Then you want to add that to the derivative of the y component, which features a product of two functions, so we will have to use the product rule here. We'll have the first function, e to the power of 2t, times the derivative of the second. The derivative of cosine is negative sine. Then we add that to the second function, cosine t, times the derivative of the first, so we have 2 e to the power of 2t. All that is multiplied by j. Then we add that to the derivative of the z component. Once again, we have a product of two functions, so we need to use the product rule. We'll have the first, which is e to the power of 2t, times the derivative of the second. The derivative of sine is cosine. And then we will have plus the second function, sine t, times the derivative of the first. So we have 2 times e to the power of 2t, all multiplied by k. Now let's simplify. I'm going to pull out the common factor of e to the power of 2t from these two terms as well as these two terms, and I'm going to reorder these two terms so that the negative one is second. All right, so this is equal to 2 times e to the power of 2t times I plus e to the power of 2t times 2 cosine t minus sine t, right? Don't forget about that 2 being multiplied by cosine t. That is all multiplied by j. Then we have plus e to the power of 2t times cosine t plus 2 times sine t k. All right, so that is the derivative of our vector function. Now let's find the magnitude of it. That's what we need for the denominator here, as well as for finding the unit tangent vector, which we'll need for the numerator. So the magnitude of r prime of t is equal to the square root of the sum of the components squared. And I'm going to square all of them right away. I'm not going to waste time writing out that we're going to square each of these components. I'm just going to square them right off the bat. So 2 times e to the power of 2t squared is 4 times e to the power of 4t, right? When you square e to the power of 2t, you multiply the exponents. So 2t becomes 4t, and then you'll have plus e to the power of 4t times this quantity squared. So we have 2 times cosine t minus sine t squared plus e to the power of 4t times this quantity squared. So we have cosine t plus 2 sine t squared. Now, to simplify, the first thing that we can do is pull out a common factor of e to the power of 4t from each of these terms, and then we can take the square root of it, and that will get us e to the power of 2t. All right, I will write an intermediate step just so I don't lose anybody here. We have e to the power of 4t times 4 plus these two quantities squared. And I'm actually going to do that right now, okay? We're going to put all of that in this quantity that we just pulled e to the power of 4t out of. And so to square a binomial, like what we have here quickly, you square the first term, add that to the two terms multiplied together, but multiplied by 2, and then add that to the last term squared. So doing that will give us 4 times cosine squared t minus 4 times cosine t sine t plus sine squared t plus cosine squared t plus 4 cosine t sine t plus 4 sine squared t. Okay, these three terms came from squaring this quantity, and these three terms came from squaring this quantity. Now, we have some terms that cancel out. We have negative 4 cosine t sine t and positive 4 cosine t sine t. They're the same term, but one is negative and one is positive, so they combine to be 0. Also, we have sine squared t plus cosine squared t. Those two terms will combine to be 1 using the Pythagorean identity for sine and cosine. So if we simplify here, this is equal to e to the power of 2t, right? We're just taking the square root of both parts here. The square root of e to the power of 4t is e to the power of 2t, and then that is multiplied by the square root of 4 plus 4 cosine squared t plus 1 plus 4 sine squared t. All right, and then what you could do next is pull out a common factor of 4 from 4 cosine squared t and 4 sine squared t, and you'll be left with cosine squared t plus sine squared t, which is equal to 1, and that would be multiplied by 4. All right, so just reordering the terms here, if we add 1 to 4, that will give us 5. So I'm just going to go ahead and change that right now. We have 5 plus 4 times cosine squared t plus 4 times sine squared t. So if you pull out that 4, you'll get this 4 times cosine squared t plus sine squared t, and those two terms are equal to 1. So this is equal to e to the power of 2t times the square root of 5 plus 4, which is 9. So the square root of 9 gives you 3. So this is equal to 3 times e to the power of 2t. That right there is not our final answer. That is just the magnitude of the derivative of our vector function. Okay, we're going to need that for the denominator of our curvature formula, but we also need it to find the unit tangent vector. And so let's find that next. Remember that the unit tangent vector, t of t, is equal to our vector function r prime of t, or the derivative of our vector function, I should say, divided by its magnitude. All right, so let's do that here. We're going to be dividing this vector function by its magnitude. And notice that when we do that, we're going to be dividing each of these components by e to the power of 2t, and that is a factor in every single one of those components. So that's just going to get canceled out. I'll write it out here anyway so you can see what's going to happen. T of t will be equal to 2 times e to the power of 2t times I plus e to the power of 2t times 2 cosine t minus sine t j plus e to the power of 2t times cosine t plus 2 sine t times k. That's just our vector function r prime of t, but then we're dividing it by 3e to the power of 2t. All right, and so that e to the power of 2t cancels out with each of those e to the power of 2t's that are factors of the x, y, and z components of that vector. So simplifying, we just get 2/3 times I plus 1/3 times 2 cosine t minus sine t plus 1/3 times cosine t plus 2 sine t. All right, now really I could have pulled that 1/3 out to the front, but I'm not going to worry about it too much. We'll take care of that later when we take the magnitude of the derivative of our unit tangent vector. For now, let's just find the derivative of our unit tangent vector. So that would be capital T prime of t. The x component is just a constant, so the derivative is 0. So we have 0i. And then we have 1/3 times the derivative of these two terms. So we have 1/3 times the derivative of cosine, which is negative sine. So we have negative 2 sine t minus the derivative of sine, which is cosine. And that is multiplied by j. And don't forget the j in the vector up here. I just noticed that I forgot that. Let me put that in there. Now we're all good to go there. There's a lot to keep track of here, so make sure you don't miss those unit vectors like I just did there. You want to remember all your i's, j's, and k's, but then we want to add this to the derivative of the z component. So we'll have 1/3 times the derivative of cosine, which is negative sine, plus 2 times the derivative of sine, which is cosine, and that's multiplied by k. Okay, now we're almost done. All we have left is to take the magnitude of the derivative of the unit tangent vector, and then we can plug that along with this magnitude into our curvature formula. So let's do that next. If we take the magnitude of t prime of t, that will be equal to the square root of the sum of the components squared, and the x component is 0, so I'm not going to bother with that, which means I'm just going to be squaring these two terms. And so doing that in one step here, we're going to have 1/9 times the quantity negative 2 sine t minus cosine t squared plus 1/9 times negative sine t plus 2 cosine t squared. Okay, so I squared both of those components. 1/3 squared is 1/9, and then those quantities are squared. Now, unfortunately, we still have a little bit of work to do here. We have to square these two quantities. So we're going to use that trick that we used before when finding the magnitude of r prime of t. We will have to square the first term, add that to the two terms multiplied together, but multiplied by 2, and then add that to the last term squared. We will have to do that for both of these quantities so that we can simplify them as much as possible. All right, so here's what we get. This will be equal to the square root. And by the way, I'm going to pull out that 1/9. You could pull out the 1/9 from both of those two terms, and the square root of it would be 1/3. So I'm actually just going to write that outside the square root at this point. We'll have 1/3 on the outside. And now if we square both of these quantities and get all of their terms, we'll have 4 sine squared t plus 4 sine t cosine t plus cosine squared t plus sine squared t minus 4 sine t cosine t plus 4 cosine squared t. Now what we have here is very similar. In fact, it's pretty much the same exact thing that we simplified when finding the magnitude of r prime of t. So I'm not going to spend a lot of time on this. I'm just going to tell you what happens here. Notice that we have a positive 4 sine t cosine t and a negative 4 sine t cosine t. Those are going to cancel out. They're gone. Then right here we have cosine squared t plus sine squared t. That's equal to 1. And then over here we have 4 sine squared t and 4 cosine squared t. Pull out that 4, what you're left with is a quantity of sine squared t plus cosine squared t, which is once again equal to 1, so you have 1 times 4. All right, so this part right here and this part right here combine to be 4. So what we're left with here is 1/3 times the square root of 4 plus 1. That's it, okay? That is going to be equal to the square root of 5 times 1/3, so we have the square root of 5 divided by 3. That is the magnitude of the derivative of the unit tangent vector. Okay, so now we have both of our magnitudes needed to calculate the curvature. So let's do it. The curvature k will be equal to the magnitude of the derivative of the unit tangent vector, which is the square root of 5 divided by 3. So we have the square root of 5 divided by 3, and then you're dividing it by the magnitude of the derivative of the vector function. So we have 3e to the power of 2t. All right, so 3e to the power of 2t. So really to simplify this, you just want to multiply those denominators together, and k will be equal to the square root of 5 divided by 9 times e to the power of 2t. All right, so that is the general expression for the curvature of the space curve in terms of t, in particular this space curve. But now let's find the specific curvature at t equals 0. To find that, we just have to plug 0 in for t in this curvature expression. So at t equals 0, k is equal to the square root of 5 divided by 9 times e to the power of 2 times 0, right? Just replace t with 0, and 2 times 0 is 0, which means we have e to the power of 0, which is just equal to 1. So that denominator just becomes 9. All right, that is the value of the curvature at that point 110 for this space curve. Okay, so a pretty lengthy problem, and that was mainly because of all of the simplification we had to do for the two magnitude calculations, and the fact that we had to keep them in terms of t for part of our answer, right? We needed to find the curvature in terms of t, which is what we have right here. If you didn't have to do that, if you just needed to find a specific value of the curvature, in other words, if we just wanted to find this right here, you could have skipped a lot of this simplification work, because what you could have done is once you had r prime of t and capital T prime of t, you could just plug 0 right into those two vectors and then take the magnitude of those two vectors and use that for this calculation. You could have found r prime of 0 and capital T prime of 0, taken the magnitudes of those constant vectors and used the results for this formula, and that would save you a lot of time, okay? But once again, that's just if you only need to find a specific curvature at a point, not the curvature at a point and the general expression in terms of t. If you have to find that general expression, then you have to do all of that work that we did in this problem. Okay, let's move on to a different example. Here we want to find the curvature of the space curve at the point 2, 4, 2. And our vector function that represents the space curve is r of t is equal to t times I plus t squared times j plus t cubed divided by 4 times k. All right, so a couple things to take a note of here with this problem is that we only need to find the specific value of curvature at a point. Okay, we don't need to know the general term or the general expression for the curvature. We just want to know the curvature at a specific point. So that's going to make things a lot easier for us when we go to do the work. We can plug in the corresponding value of t a lot sooner and save ourselves a lot of pain. Now, before we do that, we have to decide how we're going to calculate the curvature here. What formula are we going to use? And based on our vector function here, what do you think makes sense? We definitely don't want to use the formula for when our vector function is in terms of the arc length parameter, because we don't have that here, right? This vector function is in terms of a different parameter t. It is not in terms of the arc length parameter, and we don't want to go through the process of reparameterizing it. That would just be a whole lot of extra work we don't want to do. So we're not going to use the definition of curvature. We also don't want to use the formula for when we are given a plane curve in terms of a function f of x, because that's not what we were given here, right? We have a space curve with an x, y, and z component, and it wasn't given to us with a function f of x, all right? That's not a thing for this vector function. And so our only option are those two formulas that are for a vector function r of t. And in this case, the components of our vector function are polynomial expressions. They are nice little algebraic expressions, and so we can actually make use of a formula that we have not used yet in this video. We're not going to use the formula we used in the previous two examples. Instead, we're going to use that formula that involves the cross product. And that formula looks like this. The curvature k is equal to the magnitude of the cross product between the first and second derivatives of our vector function, and that's divided by the magnitude of the first derivative cubed. Okay, so to get started here, what we want to do is find the first and second derivatives of our vector function. So starting with the first derivative, r prime of t, that will be equal to the derivative of these components. Derivative of t is 1, so we have I, plus the derivative of t squared, which is 2t, that's multiplied by j, and then the derivative of t cubed, multiply that 3 down, subtract 1 from the exponent, and we get 3/4 times t squared. Don't forget about that 4 in the denominator. And that is multiplied by k. All right, now let's find the second derivative. We'll take the derivative again and get r double prime of t is equal to 0i, right? The derivative of a constant is 0. Then the derivative of 2t is 2, so we have plus 2j, and the derivative of 3/4 times t squared, you want to multiply that 2 down, so you'll have 6/4 times t times k. But now you can reduce 6/4 to be 3/2, so I'm going to do that here. We'd have 3/2 times t. Okay, so now here's where you want to take advantage of something in this problem. If we just wanted to find the general expression for curvature, we would have to work with these vectors as they are in this cross product. But we can save ourselves some time here because we only want to find the curvature at a specific point. So if we can figure out the value of t that corresponds to this point, we can plug that value of t into these two vectors now and take their cross product, and that will be a whole lot simpler, okay? That will save you a ton of time. So if we're looking at this point here, what value of t corresponds to this point for this vector function? To figure that out, just set one of the coordinates equal to the corresponding component. So if we look at the x coordinate here, 2 would be equal to t when t equals 2, right? That's the only way that that happens. You will get an x coordinate of 2 when t equals 2. All right, so that was actually a pretty easy one to figure out. We just set 2 equal to the x component, and right away you get t equals 2. That is the value of t that corresponds to this point for this vector function. So what we want to do is plug in 2 for t in these two vector functions, and then use them in that cross product and the magnitude of the derivative of the vector function. All right, so starting with the first derivative, we'll have r prime of 2 is equal to I plus 2 times 2, which is 4. So we have 4j, and then plus 2 squared times 3/4. 2 squared is 4, so we have 4 times 3/4, which just leaves us with 3. So we have plus 3k. Okay, so that is r prime of 2. Then for r double prime of 2, we want to plug 2 into the second derivative, The x component is still 0. That doesn't change. We have 0 times I. And the y component is a constant, so it's still 2. We have 2 times j. And then for the z component, we can plug into and have 3 halves times 2, which just gives you 3. All right, so we have 3k. Okay, so now our curvature here, the way we're going to calculate it is like this. We're going to take the magnitude of the cross product of r prime of 2 with r double prime of 2, and then divide that by the magnitude of r prime of 2 cubed. That's how we are going to calculate the curvature here, because we just need the curvature at a specific point. We don't need to work in terms of t for the entire problem. We can work with the specific vectors that would correspond to that value of t. All right, so starting with that cross product, we're going to be taking r prime of 2 cross r double prime of 2. So if we set up our 3 by 3 matrix here, we have I, j, and k, and we'll have the components of r prime of 2, which are 1, 4, and 3. And then the last row will have the components of r double prime of 2, which are 0, 2, and 3. So now, if we calculate this cross product, we'll block out the I column and then calculate a 2 by 2 determinant. So 4 times 3 minus 3 times 2. 4 times 3 is 12, 3 times 2 is 6. So we have 12 minus 6, which gives us 6 times I. Then we subtract the j term. So we'll cross out the j column. Then we have 1 times 3, which is 3, minus 3 times 0, which is 0. So 3 minus 0 is 3. So we have 3j. And then plus the k term, cross out the k column. 1 times 2 is 2, minus 4 times 0, which is 0. So 2 minus 0 is 2. So we have 2k. All right, now we need the magnitude of that cross product. So if we take the magnitude of r prime of 2 cross r double prime of 2, we will get the square root of the sum of the components squared. So we have 6 squared plus negative 3 squared plus 2 squared. 6 squared is 36. Negative 3 squared is 9. 2 squared is 4. So if we continue the work up here, we'll have the square root of 36 plus 9 plus 4. 4 plus 36 is 40, plus 9 is 49. So we get the square root of 49, which is 7. So the magnitude of the cross product of these two vectors for the numerator of our curvature calculation is 7. So that's good. Now we just need to calculate the magnitude of r prime of 2, this vector right here. So let's do that yet. I rearranged our work a little bit, so our vector r prime of 2 is over here now. But if we calculate its magnitude, the magnitude of r prime of 2 is equal to the square root of the sum of its components squared. So we have 1, 4, and 3. So 1 squared plus 4 squared plus 3 squared. And then simplifying, 1 squared is 1, 4 squared is 16, 3 squared is 9. So this gives you the square root of 1 plus 16 plus 9. 9 plus 1 is 10, plus 16 is 26. And you can't simplify the square root of 26 in any way. So I'm just going to keep it like that. And so now all that's left to do is plug these two magnitudes into our curvature formula. So this will be equal to 7 divided by the square root of 26 cubed. And then if you cube the square root of 26, you multiply it by itself 3 times. So 2 times would just give you 26, and then multiplying by the square root of 26 again gives you 26 square roots of 26. And if you want to, you could rationalize that. You could multiply the numerator and denominator by the square root of 26. I'm not going to do that here. I don't tend to rationalize my answers too much by this point in math. I don't see a problem with leaving square roots in the denominator. So I'm going to leave my answer like that. 7 divided by 26 times the square root of 26 is the curvature at the point 2, 4, 2 on this vector function. And if you really do like to rationalize, you could also write this. It would also be 7 square roots of 26 divided by 676. Okay, and so that's it for this example. The big takeaway here is that if you only need to find the curvature at a specific point, you want to plug in the corresponding value of t as soon as possible. Obviously, we needed to work in terms of t for the first and second derivatives in order to actually find them. But once we had those, with this formula, you can plug in your value of t right after that and make your work a whole lot simpler. If we tried to work entirely in terms of t, to find a curvature expression and then plugged into, it would have taken a lot longer and also been a lot more complicated. Okay, but with that, let's take a look at one more example for this video. Alright, for our last example, we want to find a general expression for the curvature of the plane curve and the curvature at x equals 0. And our plane curve is given by the equation y equals e to the power of 3x. Okay, so this problem is clearly very different than all of our previous examples. We are told right off the bat that we're working with a plane curve, not a space curve, and we want to find the curvature of that, and our plane curve is represented by an equation y equals e to the power of 3x, or in other words, y equals a function in terms of x. So there's really only one option for the formula that we can use here. We're going to use that formula that is specifically catered towards plane curves represented by functions. And that formula looks like this. The curvature k is equal to the absolute value of y double prime divided by the quantity 1 plus y prime squared, all raised to the power of 3 halves. Okay, so hopefully it's clear that this formula here we could not have used in any of our previous examples, because this formula does not work with vector functions. It works with an equation like y equals e to the power of 3x. Alright, but the process is actually pretty simple here. To set up this curvature calculation, we just need the first and second derivatives of our expression for y. Alright, so let's start with y prime. Let's find the first derivative of y. Y prime will be equal to the derivative of e to the power of 3x, which will just be itself, but multiplied by the derivative of the exponent, which is 3. So you'll have 3 times e to the power of 3x. That's the first derivative. Now let's find the second. We'll have y double prime is equal to the derivative of the first derivative. So really it's the same thing, except we're going to multiply by another factor of 3, because when you take the derivative of e to the power of 3x, you have to multiply by the derivative of that exponent. So you'll have 3 times 3, which is 9, and then e to the power of 3x. Okay, so now we can plug these two expressions into this formula to find a general expression for the curvature of the plane curve. And then once we have that, we can plug in 0 for x, and that will give us the specific curvature at x equals 0 on that curve. All right, so starting with the general expression, k will be equal to the absolute value of y double prime. So we have 9 e to the power of 3x, and then we're dividing by 1 plus y prime squared, and then to the power of 3 halves. Y prime is 3 times e to the power of 3x. So I'll write that in here, 3 times e to the power of 3x. Now, let's simplify. E to the power of 3x will never output a negative value, so we don't need those absolute value bars. We're good there. This will be equal to 9 times e to the power of 3x divided by 1 plus 3 times e to the power of 3x squared. Squaring 3 gives you 9, and then if you square the exponential part, you multiply the exponents, so you'll have 6 times x, because 2 times 3 is 6. So we have 9 e to the power of 6x to the power of 3 halves. And that right there is the general expression for the curvature of the plane curve represented by y equals e to the power of 3x. All right, now we want to find the specific curvature at x equals 0, so let's plug 0 in for x. At x equals 0, the curvature k will be equal to 9 times e to the power of 3 times 0 divided by 1 plus 9 times e to the power of 6 times 0 to the 3 halves power. Simplifying, 3 times 0 is 0, e to the power of 0 is 1, so you just have 9 in the numerator, and then in the denominator, 9 times e to the power of 6 times 0, 6 times 0 is 0, e to the power of 0 is 1, so you have 1 plus 9, which is 10 to the power of 3 halves. All right, so 1 plus 9 to the 3 halves power gives you 9 divided by 10 to the 3 halves power. Now you could leave it like that if you wanted to, but remember, the 3 halves power would be the same as taking the square root of 10 and then taking it to the power of 3. So you could write it like this. It would be equal to 9 divided by the square root of 10 cubed, which would be 9 divided by 10 square roots of 10. All right, if you multiply the square root of 10 by itself 3 times, that is what you'd get. All right, but either of these answers would be fine. I'm going to choose to stick with this one as my final answer. That would be the curvature at x equals 0, but you could also use this answer if you like. But that's that. This is the value of the curvature specifically at the point x equals 0 on this plane curve. Okay, and so with that, that is it for this example, and this was also the last example for this video, but I do have more examples available on my membership site, so if that's something that interests you, feel free to look into becoming a member. You can get all the details on my website at jkmathematics.com/plus. If you have any questions, please let me know in the comments, but if you don't have any questions, this is all I had for now, so I will see you next time.